Hello! In this video, we are going to prove the following theorem. Let a be a positive real number. Then, for all integers n, a to the power of n is a positive real number. So, to prove this, let's first remind ourselves of some things. First, for every real number a to the power of 1 is equal to a. Also, a to the power of 2 is equal to a times a. Another property of real numbers is, for every non-zero real number a times a is greater than 0. Or in other words, a to the power of 2 is greater than 0. So now let's remind ourselves of some of the properties of integer exponents that we have proven, which we will be using to prove this theorem. First, let a be a non-zero real number. Then for all integers n, a to the power of n is a non-zero real number. So this is telling us a non-zero real number to the power of any integer will be a non-zero real number. Our second result, let a be a non-zero real number. Then for all integers m and n, a to the power of m times a to the power of n is equal to a to the power of m plus n. And finally, let a be a non-zero real number. Then for all integers m and n, a to the power of m to the power of n is equal to a to the power of m times n. So now let's get into proving this theorem. To start out the proof, let's give ourselves an arbitrary integer n. From here we want to show a to the power of n is greater than 0. And to show this, we're going to split this up into two cases. Either n is even or n is odd. Let's start with a case where n is even. Well then, n is equal to 2k for some integer k. Now, since a is a non-zero real number, we know a to the power of k is a non-zero real number, according to our first result. And so, if we take a to the power of k and raise it to the power of 2, then a to the power of k to the power of 2 is greater than 0. But this is precisely what a to the power of n is going to be equal to, because we know a to the power of n is equal to a to the power of 2k. Let's flip the 2 times k around. It's just a to the power of k times 2, but then we can apply lemma 3. And this is the same thing as a to the power of k to the power of 2. And we know that this is greater than 0. So this shows a to the power of n is greater than 0. So this completes case 1. Now let's move on to case 2, where n is odd. Well then, n is equal to 2k plus 1 for some integer k. Now again, since a is a non-zero real number, we know that a to the power of k is a non-zero real number. So if we take a to the power of k, raise it to the power of 2, that will be greater than 0. Well then, what happens when we do a to the power of n in this case? Well, a to the power of n is a to the power of 2k plus 1, and according to lemma 2, we can re-express this as a to the power of 2k times a to the power of 1. Now we know any real number to the power of 1 is itself, so a to the power of 1 is just equal to a. But a to the power of 2k can be rewritten as a to the power of k to the power of 2, just like we did in the above case. So this is just going to be a to the power of k to the power of 2 times a. Now, this quantity is greater than 0, and a is greater than 0, so their product must be greater than 0. And that's it. We have shown a to the power of n is greater than 0 once again. So that covers all possibilities, so no matter what, we must have a to the power of n is greater than 0. So this completes the proof. And so yeah, that's pretty much it for this video.